Hey there, welcome physics students to another edition of Rapid Review for Honors Physics. Today we're talking about friction, and in particular, static friction. If you take a look here at this little demonstration, I have a block with a hook in it. This is actually a piece of decking material from construction of a deck. TimberTech, not a paid advertiser. I'm going to put this down here and attach a string to it so I can pull it horizontally. I'm going to pull parallel to the tabletop, and I'm pulling on it now, but not hard enough to make it move. Okay, so I've got a horizontal force, and we notice it's not moving. Let's analyze that here in the picture, right? So if I consider that situation where the book, well, it says book, but we know it was a piece of TimberTech, the book is not moving, we know that there are horizontal forces involved. And if I apply a force, as in this picture, to the left, there has to be something pulling to the right to counteract it. Otherwise, the thing would be accelerating, right? So what is that force? Of course, you know that is static friction. What's interesting about static friction is it's really smart. It knows just how hard to work to counteract my force. Be careful, I hesitated there because I don't want to use the word work. That has a very specific meaning, and I didn't use it properly in a physics sense. But conceptually, static friction gives you whatever you ask for. As long as you're not moving, if you pull with force 2 newtons, static friction contributes 2 newtons in the other direction automatically. So let's see what that looks like in a graph. If I apply a force, I'm looking at now the graph, if I apply a force, I get a friction force to match. It's a 1-to-1 relationship. That graph has a slope of 1 in units of newtons. 1-to-1 correspondence. The force of friction is equal to the force applied. By the way, that funny symbol there is my lowercase f, which you might draw like that. My wacky handwriting prevails again. So this is all it is for static friction. Now, there's a point at which it gives up. That's the maximum possible static friction. So static friction works up to a point, and I'm going to coin that phrase as a trademark here, maximum possible static friction. It's a number, okay? So there it is in the graph. Here's the maximum possible static friction, and it's a point at which any further I go, the thing's going to slip. Beyond that, just let's keep out for now, and it's not going to be static anymore, and we'll talk about that, what happens beyond that, in another presentation, right? So what affects this maximum possible force of static friction? Which is this? Oh, it's just the materials, and it's the normal force. And that's it. That's the only thing. It's maybe contrary to your expectation. You might think it depends on surface area or texture of the surface or other things. Surprisingly, at least to a first approximation, it's only dependent on the materials. So that's mu static. It depends on the materials, the 2 materials that are in contact with each other, and one can list mu static for various pairs of materials, which we do in the presentation. I once again credit the John Coley textbook for providing this information. Let's dissect the equation. The force of static friction is less than or equal to mu static times the normal force. Okay, the less than or equal to often throws people. It's helpful to remember that there is a maximum possible force of static friction, and then conceptually different, there's some force of static friction in a given situation. Very easy to get those 2 mixed up. Try to keep those separate in your thought process, and you will do well, okay? So the less than or equal to says, in a given situation, you're not necessarily going to get the maximum possible, and you're probably going to get something less than that. Okay? So that's how that equation works. The less than or equal to has a definite meaning. Okay? So I remind you here in this slide, this is just what I said, it's that the maximum possible is different than the force of static friction in any given situation. Make sure you're clear on that. The following equations follow. I'll let you look at those for a minute. I think it's not necessarily helpful to read them. But once you do, you'll be clear on the difference between maximum possible static friction and plain old static friction in a given situation. Let's move on to one more little bit of static friction. The equation that you need to know is the one I'm showing here, and then there are many, many applications. For example, you might be asked whether this ice block is slipping. It's ice on ice. We can look up that mu static if we need to. You might be asked if the wood block is slipping, or you might be asked a bunch of other things. What I'm going to do, because those questions have really interesting answers and there's a lot of calculations involved, I'm going to link to a special video that solves all of these problems in this presentation. So here, because this is a rapid review, I don't want to get into deep problem solving. I more want to talk about the approach. So look in the link in this video and you will see a link to a problem solving session that shows the answers to all of the problems that are posed here in this presentation. And that's all I have to say for today about static friction. Tune in next time for kinetic friction coming right up.